So we are launching into the first RO session of the conference on planning and the learning. Planning is a model-based approach, and the learning is data-driven. Sometimes they are presented as competing and even opposing view approaches to robot decision-making. It really doesn't have to be the case if we just remember that a model is just a compact summary of the underlying data with some loss of information. Right? It's really encouraging to see that these two great ideas for robot decision-making coming together at CoRL. And without further ado, let's have the first paper of the session, risk-aware prediction for robust planning, and it's going to be presented by Jean Mercat from Toyota Research Institute.
Thank you for the great introduction. And I'm really happy we finished on representing uncertainty right before, because it's what I'm trying to address here. So I'll just start with a motivation example. So we're in a car approaching an intersection, and there is that motorcyclist that also enters the intersection. There's a pause in the video where it seems that that motorcyclist is turning right out of the way. But there's a slight chance that it decides to cross the road, and that's what you see happening in the video. In this kind of situation, you want the driver to react to that eventuality, even if it doesn't happen and if it's very low probability. So in this kind of situation, when making plan for what the car should be doing, is it the role of the planner to capture those very unlikely events that are in the tail of the distribution? When making samples of predictions for what the motorcyclist will be doing, do we want the vast majority of our prediction samples to be a right turn here? How do we make sure that the dangerous event is within our sample set? And how do we compute risk in that situation? To answer all those questions, we propose a forecasting model that focuses its effort on important events instead of forecasting the most likely events. We define importance with the notion of risk. Risk is usually estimated and minimized during planning, but we show that there are some benefits to moving risk awareness to the lower level task of prediction. But first, let us look at the usual risk-aware planning. So it uses a prediction distribution P and a cost function to define a cost distribution. A risk-neutral planner would be minimizing the expected cost here, but a risk-aware planner minimizes the risk. Here we give the CVAR definition of risk, which is the expected cost, but only on the 1 minus sigma tail of our distribution. So it depends on the risk level sigma, and it will give a single value for the risk. This accounts for the uncertainty about the costs, and will better show the tail events that are high risk but low probability. When making a Monte Carlo estimation of that risk, all the samples in that gray area will be discarded, and the samples in that tail distribution will be averaged. This underestimates the risk, which is very dangerous. So instead, what we propose is to learn a bias distribution such that the risk can be estimated with a simple expected value. So we impose this equality and try to learn that distribution Q such that we can compute our risk this way. This imposes only its mean value. So it means that we can always find such a distribution, but many such distributions could exist. So what we train is a model that approximates the solution to a constraint optimization problem. The constraint is our risk equality, while the term to minimize is the KL divergence that you see here. And for now, let's just define it with, oh, sorry about that. That will keep our bias distribution within the bounds of the unbiased distributions. So to define the terms of this optimization problem, we use an unbiased CVE predictor, and we use it for three things. First, it can define our unbiased distribution that allows us to compute the risk, which allows us then to supervise our constraint here. Secondly, we reuse its latent space so that our prediction can be composed of a biased encoder and the pre-trained CVE decoder. And finally, we use its latent distribution representation to compute that KL divergence that I mentioned earlier. So we can bring our biased distribution close to the unbiased distribution by minimizing this KL loss. So we tested this approach in a didactic simulation where a car is running from left to right on a straight road, and the pedestrian appears at a random position, going in a random orientation with two modes of behavior: a slow walking mode in green here, and a fast walking mode in red, because it's more risky here. It leads to a near collision with the car. When we increase the risk level to our biased model, it predicts things within distribution. So it's one of those two modes, but it's the most costly one of the two. We tested this approach in combination with a planner and showed that the risk-aware prediction combined with a risk-neutral planner leads to safer plan than the usual risk-aware planner. We also tested it with out-of-distribution observation for the pedestrian and showed that our method is more robust than the usual risk-aware planning. Finally, we tested on a real scale, data set of at scale, the Waymo open motion data set. And we show good qualitative results, good estimation of the risk. And here what you see is on the left, the prediction with unbiased, so risk level 0. And the other agent in green is making a right turn. The ego is getting behind that vehicle. And it's going to be pretty safe because that green vehicle is going far. But if you're more pessimistic, increasing your risk level, you'll predict that this vehicle will turn slower. So getting behind it forces you to slow down a bit. And if you crank up completely your risk level, then you'll predict a left turn, and then the ego should probably come to a stop. So you can test that for yourself using the QR code. We have an online demo. On there, you'll see some failure case of our approach. The most common one is due to the fact that we're not giving the ground truth path of the ego to the prediction. So it might bias its prediction with respect to a different path than the ground truth that you see in green. So to sum up, we showed how we can bring risk awareness to prediction with a new prediction objective. And we show how this improves the prediction planning pipeline by making it more robust, more efficient, and safer. We supported those claims with simulation on real data sets. Yeah, I want to thank my co-author, Haruki Nishimura, that couldn't be here today. And yeah, if I'll be answering questions, and I'll also be in the poster session, room 40. So please come and have a chat.
Do you have any questions?
Yeah, so we want to go, so you can tell on the other side of the uncertainty, right? So instead of doing it online, we learn all of it. So if I need to change my function,
Then is it correct that I would need to sort of go through and collect a lot of new data to then be able to train this function Q that you learned, right?
So with a new cost function, you don't need new data. But you do need to retrain your bias model. It's only the second part. So we're using an unbiased predictor that you can keep and just retrain it with respect to that new cost, because yeah, you'll fit a risk with respect to a cost distribution, and with a new cost definition, you'll have a different distribution to fit.
Cool, thanks.
When you parameterize is it like an implicit density model like this VAE, or you have an explicit density for that?
So no, it's a sample-based approach.
Yeah.
One thing that's good with the sample-based is that you can you don't need to define your parameterized distribution. Parameterized distribution would allow you to compute risk probably more efficiently, but it means that you need to let me rephrase. Usually you have a parameterized prediction distribution, but under the cost function, you don't usually have a nicely behaved distribution of costs. So it's actually usually easier to just use a sample-based approach like we do here.
So the difference is you don't have to discard any samples, right? Later.
Yeah. So you're more efficient. Also, it's not biased because it's an expected value estimation, whereas the risk estimation with Monte Carlo like that is under-biased.
Okay, perfect.
Thank you very much. Yeah.
Thanks a lot.
There are the learning temporally extended skills as symbolic actions for planning. And the speakers will be Young actual fellow from Max Planck Institute.
Cool. Hi everyone, I'm Jan, and I'm going to show you an agent today which has low-level control capabilities and high-level planning capabilities. Sure. And our work is titled Learning Temporally Extended Skills in Continuous Domains as Symbolic Actions for Planning. So before coming to the dirty laundry at the end, I want to show you some dirty dishes. So imagine you enter this kitchen and you want to clean up. And the first thing you would probably do is to set up a plan of things you want to do. For example, first grab the dishwasher handle, then open the dishwasher, then grab a glass, place the glass in the dishwasher, and so on. And then in a second step, you would sequentially execute these plan items using your eyes and your hands. Now we're looking at some kind of environments which pinpoint the challenges which are apparent in such kind of environments like the kitchen environment, which are physically embedded planning problems. They were introduced by Mirza and others, and they embedded adversary board games into physical manipulation scenarios. And we are looking at some similar environments, which are, however, single-player board games, which are embedded into physical manipulation scenarios. And these environments have some special properties, which are that you require both high-level planning capabilities and low-level control capabilities, which are classically in classical benchmarks solely focused. So you have, for example, in OpenAI gym or DeepMind control suite, you need low-level control capabilities. Or in games such as Go and Sokoban, you need high-level reasoning or planning capabilities. And in these physically embedded games environments, you require both of them. So let me get into a bit more detail. One board game we're looking at is called Lights Out. And in Lights Out, you can push fields on a 5x5 board. And by pushing a field, you will change the illumination state of that field and its adjacent fields. And you're presented some board, and your task is to switch all fields off. And as physical embeddings, we looked at, for example, embedding this game into a reacher environment. So you can push fields through the end effector of a reacher, or by embedding it into a Jarko manipulation environment where you can push fields, or where this Jarko arm can push fields using its fingers. We also looked at a physical or real-world scenario where we play this game on an Android tablet using an actual robot. Now let me come to the architecture of our proposed agent. So on one hand, we do low-level control using skill condition policies. And on the other hand, we have a forward model which models the effect of executing a skill until termination in a state abstraction of this environment. And here the state abstraction maps from the full state of the environment to the board state of this Lights Out game. Now, if we want to solve a task, for example, play the game, we would first plan over like a sequence of skills we want to execute sequentially to reach our goal. So here we start with some state of the Lights Out game, map it to our symbolic representation, and then plan using the learn forward model a sequence of skills we need to execute to reach our target. And then secondly, we would execute these skills sequentially using our learn policies. How do we learn this? So we learn both the forward model and the skills jointly. And first, let's look at what is actually a good set of skills we would like to learn. So we want these skills on one hand to be diverse. So if we have two different skills here, it's 1 and 2. We do not want them to cause change in the symbolic state, which is the same. So this is like a bad example. And a better example would be that they cause different changes in the symbolic state. Secondly, we want skills to be predictable. So if we apply skill 1 twice, we want the change in symbolic state to be the same. So here it's different, that's bad. And here it's same, that's good. And we can measure or formalize this through entropies. So in the first case, we want the entropy of the target state to be high, given the initial state. And if we, in addition, condition on the skill that was executed, we want the entropy to be low. So we want the uncertainty to be low. We want to well know in which state we will end up when executing that skill. So the learning objective would be to maximize the first entropy and minimize the second, which is identical to maximizing this mutual information term here. So this then yields a learning signal for both the skills and for the forward model. Prior workers employed a similar objective, however, for low-level skill discovery, for example, variation intrinsic control, diversity is all you need, or dynamics aware unsupervised discovery of skills. Here I show you some example of the learning progress on our real robot platform. On the left, you see the skills that were executed colored by the skill index. And on the right, you can see the setup with the tablet and the robotic arm. And at the beginning of training, the skills basically cause random pushes on this Android tablet. And when training this over time, we see that gradually these skills relate to pushing individual fields on that board. So we never tell it to do this, but it learns to execute game moves through this mutual information objective. And after some time of training, so in this case, it's roughly, so here it's 47 hours, it's quite a long time actually. But we see on the left that these skills then relate to pushing individual fields on that board. Let me come to the numerical results. So we were looking at 6 simulation environments and 1 real-world environment. And in these simulated environments, our presented agent is able to solve these physically embedded games with high success rate of over 90%, in contrast to the baselines we looked at, which were soft actor critic and hierarchical actor critic, which have lower performance of these 6 environments. In that real-world environment, after roughly 43.5 hours of training, we exceed a success rate of 95%. Okay, now let me come to the dirty laundry. So one assumption we make is that the state abstraction function mapping from the full state to the abstraction is known. And in future work, we want to learn this. The second point is that occasionally not all skills are found within a step limit we set of 10 million environment steps. And we believe that it may need more sophisticated low-level exploration to find all skills reliably. A third point is that the planner we use, which is just a best first search planner, exceeds the 5-minute threshold for a solution depth of 9. So if you require more than 9 steps to solve the game, it will take you more than 5 minutes to plan this. But yeah, if we believe that if we employ more sophisticated planners or use some heuristics, that we can drastically improve on this. So let me summarize. The presented agent seeds, learns skills and symbolic forward model jointly, and allows for high-level reasoning and low-level control. It solves the proposed physically embedded games with high success rate in contrast to the baseline agents. And we show successful application to a real-world robotic system. Thank you for your attention, and I'm open for questions.
Oh, thanks so much for the nice presentations. So one question I have is that I feel like the states that you have are sort of homogeneous, like they don't really differ that much aside from their abstract meanings, but like in terms of the sensory input, they're similar. Like, how do you imagine your approach extends to those that involve more diverse visual changes or any perceptive changes?
Do you mean the?
Like, for example, like in kitchen, you have a lot of, yeah, right.
You're right. So in more complex environments where there's more required than pushing as skills, we believe that it's even more important to have like a low-level skill discovery objective to really detect these different low-level skills, because in this approach, the only exploration which happens is through the noisy execution of the soft actor critic low-level agent. However, there's no low-level skill diversity enforced, and we believe in an environment like a kitchen where we really have very diverse skills, which also are diverse in not only the symbolic effects they cause, but also in their low-level behavior, that it's even more important to have some additional low-level diversity objective or something.
Thanks, Jan, for the nice presentation. I was wondering, how does the system deal with failures of the low-level module, of the low-level policies?
Actually, so we did not kind of make it especially hard by introducing additional noise terms or something, but we observed that, for example, on this tablet, sometimes there appear like warnings that the battery level is low or something, and it can cope with that. It just, if a push does not yield a change in the symbolic state, it will just keep pushing and like push this warning away, and then put in like the next push works. So this is what we observed.
Thank you for the presentation. I just had a question. You said that that the forward model and the skill execution model are both trained simultaneously. So at the start of training, would you not have a mismatch of the final state that's reached by the symbolic model and the actual execution of the skill? How did you deal with that?
Can you repeat that? I didn't get it.
You mentioned that your forward model was trained simultaneously with the skill execution model. And at the start of training, would there not be a mismatch between what the skill model actually achieves as the final state and what the forward model predicts as the final state? And how did you deal with that?
Yeah, there are always mismatches, and to be able to learn this offline, we found that it's very important to have some kind of relabeling actually. So we execute skills, but then if a skill actually does something else, we can find this out through the forward model we have already learned and change the label of the skill that was actually executed to a label that would have been more likely.
Okay, thank you.
All right, thank you, Jan.
Welcome.
Our next stop is going to be meta-learning priors for safe Bayesian optimization, and the speaker is going to be Jonas Rothfuss from ETH Zurich.
Perfect. There we have it. Yes, as you might have guessed already from the title, this talk is about safe optimization, where we have an objective which we want to minimize and a safety constraint. Yeah, these are typically unknown function, like in a standard black box optimization setting. And for example, we can evaluate this function by running an experiment on our robot and doing some measurement. So we can evaluate these functions, but of course it's costly to do this. Yeah, and the key feature of this problem is that we never want to violate this constraint, even not during the process of optimization. Yeah. To give some examples where this is relevant, for example, in this work, we have worked with some collaboration on high precision linear robots, where we want to tune the parameters of this robot, which is used in semiconductor industry to kind of in these lithography machines, and we want to move it as fast as possible with micrometer precision. But the load that is on top of it, usually the wafer, should never be subjected to vibrations above a certain level, because otherwise we can throw away everything that is supported on the robot. Another examples are drones, where we might also want to optimize some stuff, but of course don't want to crash the drone in the process. Yeah. So how does this look in practice? For example, when we do controller tuning, yeah, we would set some controller parameters initially where we're confident that they don't violate the safety constraints. Yeah. And we would do our measurements, observe the kind of the target, what we care about, also the constraint value. Usually these measurements are noisy. And then we start to model these two functions, the target and the constraint function, with a Gaussian process. Yeah. And now we have to kind of carefully work our way out and expand the set of safe parameters. Yeah. And be careful that we never get into these regions. Here, for example, to the right at the bottom, where we would violate the safety constraint. Yeah, and as you can see, like the efficiency and also the safety of this approach hinges a lot on the validity of the GP that is used. We look at a particular problem here where yeah, we want to do meta learning or transfer, so we assume that data from some previous optimization runs, for example, under different conditions where we have different loads on our robotic platform, or we have different tools attached, are already there. And yeah, this data can be also highly non-IID. And then we ask, how can we make use of this previous data to make the safe Bayesian optimization more efficient? Yeah, and we do this in two steps. Step number one is we look at how can we choose good but safe kernel parameters for our GPs. And the second step is, can we go one step further and actually meta learn more expressive GP prior, yeah, that can incorporate more inductive bias about the problem we want to solve. Yeah, so let's start with step number one. Yeah, yeah, it's very difficult to choose the right kernel parameters here, for example, for an RBF kernel. Yeah, the kernel variance and the length scale. If we go to conservative, yeah, we're of course safe. Yeah, if we choose the length scale very small, then the safe set will expand super slowly, and it will take us ages to optimize, for example, our controller. Yeah, but on the other hand, if we go too crazy about it, the safe set expands super quickly, and we might run into some issues that we query some unsafe configurations and might damage the payload or the robot. Yeah. So what we would like in practice is we want to find a safe sweet spot where our GP parameters are still give us safety, but we're also fairly efficient during the optimization. Yeah. And now the question is, how can we choose these parameters? Yeah. And here we can make use of this meta training data, yeah, from previous runs. And in the paper, we come up with some metrics that are focused on the uncertainty estimates of the GP in response to the kernel parameters. And we can write this down as a constraint optimization problem, yeah, to find good parameters. Yeah, what we want to do is we want to maximize the sharpness of the uncertainty estimates. So we want to have them tight and snug around the function so that we get efficient optimization. But on the other hand, we have to guarantee that these uncertainty estimates are valid. Yeah, so we want them to be calibrated so that the optimization is safe. Yeah, and what means calibrated? So for example, here, when we take a 95% confidence interval, we want that at least 95% of the data is contained in it, like test data. Yeah, here at the top, this would be satisfied, but at the bottom, this would not be satisfied and would violate this constraint here, for example. Yeah. And then in the paper, we also come up with like a dedicated strategy on how to find these parameters fairly efficiently. But we can talk more about this in the poster session. In the last 2 minutes, I want to talk about how we can go one step further and even get more inductive bias into our GP priors. In particular, we can parameterize them as neural networks, yeah, and kind of meta learn them. But now we have to be very careful, because if we meta learn, we might also get unreliable uncertainty estimates and run into this safety problems. Yeah, so what we do is we try to fit them to the data we have, but also regularize them towards the vanilla GP prior, yeah, for which we have chosen the parameters in the previous stage. Yeah, so, and this regularization is happening in the function space directly on kind of the marginals of the stochastic process, so that we can ensure that uncertainty estimates are calibrated. Yeah, and here you can see kind of how this looks. On the left, we have a vanilla GP, and on the right, we have the meta-learned GP prior, which gives us a bit more inductive bias and speeds up the optimization, but we still get reliable uncertainty estimates, which you can see here at the right bottom. And in the end, I want to show you some result when we employed this technique on this robot for safe, so where we optimize the PID controller gains. And you can see that if we meta-learn here at the bottom, we can actually improve the efficiency of the Bayesian optimization by quite a bit. And at the same time, we stay safe and get no violations by this regularization and by carefully choosing these parameters as discussed. Yeah, so in summary, what we do is we introduce some data-driven method for choosing safe kernel parameters. And also we discuss how to meta-learn a more flexible GP prior, which is still safe and abides these very strong conditions which we need to ensure safety, that our system doesn't get, our robot doesn't get damaged.
So really fascinating work. And so I'm wondering, this Bayesian optimization is always a little troublesome when the dimensionality becomes higher. Can you give us a bit of an idea of how far did you go up and where do you see the limits?
Yes, this is certainly an issue. And I think this issue becomes even worse with the safety constraints. So this stuff definitely does not work on more than, let's say, 10 dimensions. Yeah. So, and this is with the safety constraint, it's even worse, because in addition to the normal Bayesian optimization, where we can just query all over the place, we have to expand the safe set. Yeah. So this gets worse. And I totally agree. This is with these strong safety standards, which we have here under these assumptions, we cannot get this reasonably to work for high dimensional problems. Yeah, this is an issue, and we haven't solved this.
Thanks.
Can you describe a bit about your the acquisition function you use and whether you have any regret analysis on the safety constraints in there?
Yeah. We use here various methods. So this kind of, we focus on how to choose these GP parameters correctly. Yeah, because usually there has been a bunch of prior work like SafeOpt or also Goose, which assume that these parameters are chosen appropriately, which of course is never the case in practice. And so we focus on how these parameters can be chosen correctly so that safety is guaranteed. So we're kind of agnostic to the algorithm that is used in the end. We have in the results I showed on the previous slide, which you can't see anymore, we have tried two different approaches. Yeah, and under basically when we do this kind of choose the parameters as discussed, we can just apply the regret analysis of these papers and basically get their guarantees. Yeah. So this is basically looking at the assumptions previous papers have made, which are not fulfilled in practice, and trying to kind of work our way around it so that we can actually employ this in practice.
Right. Thank you, Ines. Our next stop is do as I can, not as I say, running languages in robotic affordances. The speakers are Brian Hichter and Carol Hausman from Google.
Hello, hi everyone. I'm Carol.
I'm Brian.
and we wanted to tell you a little bit more about our work called SayCan. This is work done by a lot of authors that you can see on the slide here, from Robotics at Google and Everyday Robots, and we are happy to be presenting on their behalf. So when starting this work, we wanted to focus on this question: how can we make robot learning more useful? And what we meant by this is we want to have a simple mobile manipulator, not necessarily a full-blown humanoid, just a simple robot. And we want to be able to talk to it and for it to carry out these tasks. So things such as, I spilled my drink, can you help? Or can you bring me some spicy chips and something to wipe my hands? Or I'm feeling tired, can you make me a latte? And if we want this robot to understand all the intricacies and nuances of the language, and then to carry out these tasks if it can. So it should be also aware of its own affordances and what it can actually do in the world. So with this goal, we looked at our results that we had at the time in robot learning. And we were able to learn a lot of different simple manipulation skills in this sort of constrained bin-like setting, where we have robots that can do picking, placing, moving objects, stacking, covering, simple manipulation skills. And we were quite proud of this work. But when we compare this to our goal where we want to be, this is still a really big gap. So we started thinking about what we can do so that we can bridge that gap as much as possible. So what's like the high leverage thing that we can introduce here that will bridge that gap? And we thought really hard about this. We couldn't really figure it out. So we did what every self-respecting researcher would do in this situation, and we asked ChatGPT. And ChatGPT very confidently said that the answer that we're missing is large language models.
But there's a few problems before we can just directly apply large language models on robotics. So if we ask some state-of-the-art ones right now, they respond in what's very reasonable ways if you're just trying to maximize language response. So things like using a vacuum cleaner, finding a cleaner, or taking credit for the spill. But these aren't things that a robot can necessarily do. So what we really need to do is make sure that these language models speak robot. They do to output things that the robot's actually capable of executing. The other thing is, if I asked you this question and you had your eyes closed, it's sort of hard to reason about what's actually available in the scene. So if you then open your eyes and see this, well, probably bring the sponge is what you should do. The language models have the same problem, and really what we need to do is make it so these language models can see. One way to do this is to leverage all the experience of robots. So we use robotic affordances to do this. To walk through how we actually do this, at first we query the language model with something like put the apple on the table. And then instead of using the generative output, so like the highest likelihood thing, we instead constrain the way it can respond into things that a robot can specifically do. So like finding something, picking things up, placing things. And then we look at the probability of those as a completion for that statement. So this is basically how useful it is. But again, this doesn't solve the seeing. This is only the speaking robot. So we need to get somehow this like vision, this like embodiment into the equation. So we use affordances here, which is basically the probability that you'll be able to execute that command. And so we can see here the score of pick up apple is pretty low. There's no apple in front of us, but instead find apple has a higher score. So we combine these two scores. We have basically useful, the probability that the task is useful to execute some high level instruction, and the probability that you're going to be able to do it. Together, we select find apple. We then execute it, roll it out in the world, update the query so that the language model knows what's happened, and then update the world state so the affordance model knows what's happened, and so on and so forth. So to really like drive home the message, the language model is using all of its experience from internet scale data of order and semantic and world knowledge to say what's useful. On the other side, the affordance model is saying, what can the robot actually do given the state of the world, given its abilities? Together, we get this say-can weighted combination.
So now we actually wanted to show it to you how it works in the real world. So it's time for a live demo. This will be demo happening in Mountain View. You can see Brian here typing in a chat, in the robot chat, asking the command that I specified at the beginning. So can you bring me some spicy chips and something to wipe my hands? On the other side, we have Fei Xia, one of the co-authors, who is connecting with us from Mountain View. So we are doing this demo across the globe, communicating to the robot, and let's see if it can carry out that instruction. Here in the chat, you will be also able to see what the robot is responding. This is how SayCan is planning. Right now, it's actually clarifying. Do you want to have it be delivered at your desk or another location? Brian specified it's at my desk. And then you'll see how the language model reasons about the different steps, and we'll see if the robot can succeed at this.
So while that's happening, I'm going to keep going through slides, and you'll maybe be somewhat distracted, but I'll talk about some of the results that we found. So for the paper, we did 101 instructions. Overall, we got 84% planning rate. We did this over a variety of skill types, so really long horizon ones, shorter horizon ones. We actually had some that were 50 plus navigation and manipulation skills in a row. So this was like clear everything off the counter, throw away everything in the kitchen. Importantly, this grounding actually halved the overall error of the language model. So it's really important that we ground our models in the real world in what the robot can do.
In the meantime, you can see the robot just found jalapeno chips, which are spicy. Now it's trying to grasp it.
One thing that we're super excited about is that we can sort of ride the wave of language models and all the progress there. So as we get a better and better language model, our performance improves, is what you can see on this plot. We can also take algorithmic breakthroughs of language models, such as chain of thought prompting, get performance boosts just basically for free. Then we can do, at the end, sort of abstract tasks, tasks that require reasoning, like 2 different sodas, they have to be different ones, long horizon ones, or even multilingual just sort of falls out of the language model. The other thing is you can actually go and play with this. So we've open sourced a Colab. It's just a tabletop environment rather than the full robot. But it at least allows you to sort of see the capabilities of the language model and the overall algorithm. We also can like show a bunch of decisions that it's made in this interactive website.
Right. So while the robot is, I think, just found the napkin dispenser, and now it's going to grab a napkin because you wanted to wipe your mouth with something. So one thing that I wanted to add about this demo is that this is being done in a previously unseen kitchen. So this is a kitchen in a Google office building, and we didn't train the robot in that kitchen. In the meantime, let me tell you a little bit about dirty laundry. So one of the things that we found out is that affordances, that aspect of SECAN, can be actually fairly tricky to get to work reliably. So they can be quite brittle. This is right now, I think, one of the bottlenecks of the entire system. The way we train them is using value functions with sim-to-real reinforcement learning. But I think there might be better ways to do this so that the robot can, in any situation, be aware of what it's capable of and answer it confidently. Secondly, in the current setup, grounding is done completely separately from the large language model part. So we have a separate affordance model, and that means that there is a little bit of inefficiency. So first, the language model comes up with the entire plan or what it's trying to do, and then the affordance model has to score that. I think there's a way better way to do this where both of these things can be done by the same model. Thirdly, as in any large language model work, there is some prompt tuning that is required. In the appendix of our paper, we show some ablations demonstrating how many examples you need in the prompt to get what kind of level of performance. In the meantime, we can see that our robot said, "It was a pleasure assisting you. I am done." And here is a proof. Faye is showing. Yeah, Faye, can you demonstrate a napkin and a chip bag?
And one thing that's really nice is it can actually say it's done, like it knows that it's kind of accomplished the full task.
One more real quick point is that you might have realized this already, but the failure right now is not being communicated to the large language model. So if there was something wrong with this plan and the robot failed at some point, it wouldn't be able to replan as it's currently constituted. So it's all done open loop. However, we've done some work since then called inner monologue, where you can have multiple models communicating in natural language, and some of them might be describing the scene, telling the robot what is happening, whether it failed or not, and they're talking to each other like a monologue between these different robots, describing what is happening and drawing conclusions from that. Right, so to quickly summarize, I think we're running out of time. We show that large language models can provide task grounding, but it's not a one-way street. So robotics has a big role to play here, and robotic value functions in this case provide real-world grounding, which is really crucial because these large models are not grounded in the real world. Thirdly, that entire setup is fairly extendable. So you can add any new policy to it. It doesn't even need to be a learned policy. It could be a scripted policy, a teleoperated thing. You can add it as long as you have an affordance function connected to it, and it can be incorporated into SECAN. Additionally, the nice thing about it is that it's easily interpretable. So at any decision point, you can see what the affordance model is currently thinking, what the large language model is currently thinking, and how the decision is being made and how it weighs these different options. And lastly, and I can't stress it enough, still the biggest challenge, I think, especially now, is on us, the roboticists, to figure out how to do the low-level skills. So this is still the hardest part of robotics. This is really where the robot needs to interact and do the thing. And then regardless of how well you planned around it and how talkative the robot is, it's still the hard part is the fact that the robot needs to go out and do the thing. We have some initial steps towards this. Recently we released this robotics transformer work, but I think a lot more work is needed here. And this is it. Thank you so much. We also wanted to invite you to come to talk to us at the booth, and you'll be able to ask a robot your own query, and we'll try to run it live in Mountain View.
All right, in the interest of time, we can take 2 short questions. Can I have the next speaker to set up, please? Yeah, please.
What's the difference between affordances and describing using perception in language using the model? In theory, the perception system would be able then to describe what it saw and feed it to the model that will make it a lot more interactive, reactive. And yet you have affordances. Can you compare and contrast how these two approaches?
So I think the question is, what's the difference between affordance model and a perception system that will describe the scene to you?
Yes.
Yeah, so the affordances are based on the embodiment of the robot and its own experiences. So they're not just about the environment. It's also about what the robot thinks it's able to do, given everything that it's experienced before. So for instance, if it doesn't have a hand, it can pick up the chips, even though a perception model would recognize that these are chips.
I guess like practically speaking, for like ours, if you saw an apple in the distance, you can't necessarily grasp it until you're close enough. The value function understands this, that you need to be in the right position. We actually need to be in a different position for the drawers to open than to pick. And so there's these like subtleties that would be really hard to put into a perception system in a general way.
Yeah, but do you need to talk to the model based on what you see in the scene?
So here we don't do like we don't actually describe the scene. In inner monologue, a follow-up work that's actually has a poster, I think tomorrow or the next day, we do some of that. But in general, we don't need to necessarily describe the world to the language model.
Right. Thank you, Carol and Brian. Our next talk, learning attention over driving behaviors, and the speaker is Pan Zai from the Shanghai Jiaotong University.
Hi, everyone. My name is Pan Zai. I'm here to present LEADER, Learning Attention over Driving Behaviors for Planning on Uncertainty. And I'm currently an associate professor in Shanghai Jiaotong University, but the majority of this work has been done when I was a postdoc in the US. Driving a crowd is a challenging problem, not only because of the large scale thing and also the speed of the traffic. It's also because of the complexity and uncertainty of human behaviors. A human participant in the scene can have multiple possible intentions at the same time. For example, they can intend to take different routes or have irregular intentions, such as reverse direction driving, beating the red light, and so on. And in a typical traffic scene, a self-driving car will encounter many human participants, and this will cause an explosion of uncertainty. Say that each human participant has few possible intentions, and this already creates thousands of possible combinations of intentions, and each combination also results in a continuum of motion. Now, under this great amount of uncertainty, we have to plan our own actions. Planning on uncertainty solves this following optimization problem. We first want to consider all possible future scenarios and then estimate our return under the future scenarios and choose our optimal policy that maximizes the expectation of our return. But in practice, it's intractable to consider all possible future scenarios. So state-of-the-art planners consider Monte Carlo sampling to solve this problem. Planners do a look-ahead tree search, starting from sampling a subset of possible scenarios. And then they simulate the future condition on the sampled scenarios and then search for the optimal policy within the tree. But for real-time planning, the number of samples or number of scenarios that we can effectively consider within a fraction of a second is very limited. Therefore, we have to carefully select our samples according to the importance of behaviors. Now let's discuss about the importance of behaviors with a concrete example. Here we have visualized human behaviors as trajectories, and also their probability of occurrence inferred from the interaction history. Now, typical planners regard the most likely behaviors to be the most important ones. Therefore, during planning, they sample human behaviors or intentions from the inferred distribution of natural occurrence. And as a consequence, in the tree search, more likely behaviors get sampled more frequently and their consequences are examined more carefully. And with unbounded number of samples, this approach actually guarantees optimality of planning on uncertainty, but it is unsafe because low probability events are very likely to be overlooked, but they are critical when they happen sometimes. For example, here we will have to slow down to avoid collision. And this kind of events are referred to as the rare critical events, such as a vehicle beating the red light or a child suddenly starts running. And it's very important for planners to be aware of such risks. So in order to perform risk-aware planning, we propose to explicitly consider an important sampling distribution, which characterizes how critical a behavior is to our own actions or decisions. Now, in our leader planner, we explicitly sample human intentions or human behaviors from the important sampling distribution, so that in a search tree, more critical behaviors get sampled more frequently and their consequences are examined more carefully. And we further use importance weights to unbias the value estimates so that we're still optimal with unbounded number of samples. Now, after doing this, we have actually introduced behavioral attention to the planning process. We have moved beyond reasoning about how behaviors will naturally happen. Instead, we attend more to critical behaviors that has adversarial consequences, such as collisions. And of course, the key problem here is how do we construct the attention for different driving situations in real time? And we solve this problem by learning from data. We learn an attention generator, which is a neural network that maps the inferred distribution B of natural occurrence of human behaviors to an importance distribution Q that characterizes how critical a behavior is. And of course, this is conditioned on the context of history of observations. So this is a recurrent neural network based on GRU. And we learn the attention generator in such a way that we increase the attention on adversarial behaviors of human and lower the attention on safe behaviors of human. And this is automatically achieved by constructing a min-max game between the planner and the attention generator. Now both sides share the same utility, which is the planning performance. The planner is a maximization player. Conditioned on a given Q, it has to find a policy pi that maximizes the value estimate. And the attention generator is a minimization player. It has to find a Q that minimizes the planner's value estimate. Now, when executing this min-max game, the attention generator will automatically learn to highlight the most adversarial behaviors of human in its output in attention. And then when the planner consumes the attention, it is forced to perform risk-aware planning. And while this idea of min-max game is relatively simple, the difficulty here is how to make the learning work, because now the objective of learning has a planning component, which is non-differentiable and prohibits gradient descent training. Therefore, we solve this problem by building our learner based on generator critique, which is an approach proposed in our prior work to learn general components of planners. So our training pipeline is like this. We have a forward planning pass and backward learning pass. In the forward pass, the attention generator first generates an attention or important sampling distribution, which is used by the planner to make risk-aware decisions and output a value estimate. And in the backward learning pass, we approximate the non-differentiable planning objective using a critique, which is another neural network trained to fit to the planner's value estimate. Then we use the critique as the differentiable surrogate objective to train the generator. Now, after training, we can use the attention generator and the leader planner to drive. And here's the episode discussed before as the example. And here we have actually shown the learned attention. Leader learns that a merge right behavior of the human is critical. So it learns to put more attention on it during planning or during the tree search by biasing sampling and less attention to other safer behaviors. during the planning or during the tree search. And here's another snapshot. Leader learns that a merge left behavior of human will be critical now. So during sampling, it biases sampling towards this attention inside the tree search, therefore determined to reduce the speed first and then speed up after ensuring safety. Now here are the takeaway messages. In order to tackle complex interactive environments composed by human, we have to attend to the critical behaviors of human. And we have proposed a planning approach that plans using the behavior attention using importance sampling. We have also proposed a learning approach that learns behavior attention using a min-max game. And of course, our limitations comes with our assumptions. We have assumed that the domain is safety critical, so more adversarial behaviors are more important and they require more attention. We have also assumed we know the potential, what are the potential behaviors of human, which information is relatively easy to obtain in structured environments and relatively hard to obtain in unstructured environments. And now we have used a model for both planning and learning, which means that we are going to be affected by model errors. However, because we emphasize the adversarial behaviors of others, so our planner will be more robust to model errors.
Provide more informative supervision, the goal-reaching reward function during.
And also welcome to check out more driving videos on our website and the source code on our GitHub repo.
We have questions?
Thank you for the great talk. So I had a question over here on the right. Yeah, there you go. I had a question. So if we overemphasize the safety, is it possible that there's a failure mode of being too conservative, for example, always yielding at an intersection or something?
Right. So the key is not to overemphasize on the safety. So the process of importance sampling has two parts. The first part is to bias sampling. The second part is to unbias the value estimates. So when you bias sampling, you try not to ignore the critical events, and by unbiasing the value estimates, you try not to overemphasize the dangerous events. That's how we achieve it.
Okay, thank you.
Yeah, thank you. First, a comment, I don't know whether you're aware of, but there are methods to differentiate through these combinatorial solvers or these path planners without learning a separate function like network to do it. So keyword black box differentiation. But actually my question now about this min-max game, is it possible that this game produces an effect where the natural behavior is actually completely ignored? So you're only looking at the adversarial behavior and the naturally occurring behavior is actually then sort of ignored. Is that possible or will that not happen?
That's a good question. If you don't do any regularization, then it's possible. But in importance sampling, there is an implicit assumption that the importance sampling distribution should have the same support as a natural distribution, natural occurrence distribution, which means that if there's no non-zero probability for some behavior to occur in the natural occurrence distribution, then in the importance sampling distribution, it should not be. It should also be non-zero. So in order to achieve that, we actually did a very simple way, which is to add some smoothing factor, just ensure that every behavior has non-zero probability to be sampled. That's how we do it. It's a simple way, but you can find better ways to do that too.
All right, thank you, Pampan. And so the last talk of the session is going to be generalization with lossy affordances, leveraging broad offline data for learning visual motor tasks. Unfortunately, the speaker wasn't able to get connected, so we are going to play the recorded video.
of diverse multicast data for these tasks still remains a preference. Hi, my name is Quan Fang, and I'm presenting generalization with velocity affordances, leveraging broad offline data for learning visual motor tasks. The use of broad datasets has proven to be crucial for generalization in various AI domains. However, how to effectively make use of diverse multitask data for downstream tasks still remains a grand challenge in robotics. In this work, we study how to leverage broad offline data to enable efficient learning of novel tasks. For this purpose, we combine offline RL and goal-conditioned RL. In contrast to prior work, we learned loss representations of states and goals. Such representations facilitate generalization by emphasizing on task-relevant properties of the environments while abstracting away domain-specific information. As a result, our method can learn from massive and diverse offline data without explicit rewards and adapt to temporarily extended tasks in various domains. We propose FLAP, a framework that combines representation learning, reinforcement learning, and planning. In FLAP, we pre-train 3 modules on the offline data. The state encoder that maps states and goals to the loss representation space. The affordance model that predicts the distribution of feasible states as candidate subgoals. And the goal condition policies that chooses the actions to reach the goal. To enable generalization to unseen environments, both affordance model and the goal condition policy are defined using the loss representations. Given the target task, FLAP fine-tunes the policy without any explicit reward signals. To guide the fine-tuning process, subgoals are planned with the affordance model in the loss representation space given the visual inputs. Specifically, during offline pre-training, we jointly learned the state encoder with the policy, the value function, and the Q function. In addition to the RL loss, we use a variational information bottleneck to regularize the learned representations. The variational information bottleneck quantifies the mutual information between the state space and the representation space. Minimizing these mutual information terms encourages the learned representation to abstract away redundant information in the raw sensory inputs. During online fine-tuning, we first project the initial state and the final goal to the loss representation space using the pre-trained state encoder 5. Then we use the affordance model to recursively generate sequences of subgoals as candidates in the loss representation space, conditioned on the initial state and the latent codes sampled from the prior distribution P of U. The optimal sequence of subgoals is selected through sampling-based planning with a loss function C. The cost function measures if the final goal is reached and if each subgoal in the plan is feasible from the previous subgoal. The planned subgoals are used to guide the goal condition policy to produce actions for reaching the final goal. To provide more informative supervision, the goal-reaching reward function during online fine-tuning is defined by the Euclidean distance in the loss representation space. For the real-world experiments, we use trajectories collected from various scenes through teleoperation. This training data is based on the bridge dataset. To visualize the learned representations, we sample 9 trajectories with varied camera poses, illumination conditions, objects, and motions. And we visualize the trajectories encoded by our state encoder using t-SNE. Each trajectory is projected to be a curve on the plot. The trajectories and their initial states are indicated by the corresponding colors and numbers. As we can see, using the representations learned by FLAP, semantically similar trajectories are close to each other in the learned loss representation space. As comparisons, we also plot the trajectories in the original pixel space and the representation space learned by the VQVAE. In the pixel space, we can now observe any obvious structure of the curves. In the VQVAE space, each trajectory collapses into a different click regardless of whether they are from the same type or how much of the scene changes in each trajectory. Our learned loss representation space demonstrates to have a more informative structure. We evaluated FLAP in 3 different sequential tasks in the real world. In the first task, the robot is asked to move the pot from the right stove to the left stove. After pre-training on the offline dataset, the policy achieved 12.5% success rate. The robot often misses the edge of the pot when trying to pick it up. After fine-tuning, with the selected subgoals, FLAP achieves a 75% success rate. The model-free baseline and the PDB baseline achieved 0% and 25% success rates. And the ablation method without using prior data achieved a 12.5% success rates. In the second task, the robot is asked to move the colander onto the stove and then drop the bunny into the colander. You can think of it as making a rabbit stew. The pre-trained model achieves a 25% success rate, often failing to pick up the objects. After fine-tuning, FLAP achieves a 62.5% success rate. During test time, the model-free baseline and the PTB baseline could not achieve any successes, and the ablation method achieves a 25% success rate. In the last task, the robot is asked to place a piece of sushi onto the yellow plate and then drop the knife in the pan. The pre-trained model can achieve a 25% success rate, often failing to drop objects to the right positions. After fine-tuning, the success rate increases to 50%. Again, both baselines fail to achieve any successes, and the ablation method achieved a 12.5% success rate. We also conducted a large-scale evaluation in a real-time physical simulator. The offline data set of our simulated experiments are collected by a scripted policy using privileged information from scenes with a variety of objects and camera viewpoints. After offline pre-training, we fine-tuned the goal condition policy using FLAP on 3 target tasks. We compare our results with 4 baseline methods, the ablation method that uses only target data. In all the 3 tasks, our full method consistently achieves the superior success rates. Although FLAP is a general framework, it makes 2 important assumptions. First, the state spaces of the offline dataset and the target task need to have the same dimension. Otherwise, the state encoder pre-trained on offline data cannot be applied for the target task. Second, the offline data needs to contain trajectories with structurally similar behaviors to those that are required to complete the new task, so that the affordance model can sample meaningful subgoals after being pre-trained on the offline dataset. To summarize, FLAP utilizes massive and diverse offline data for pre-training without hand-specified reward signal. It plans subgoals using an affordance model to compose a goal condition policy for learning temporally extended tasks. And it learns the loss representation to provide compact inputs to the policy, facilitate subgoal planning, and shape reward signals during online fine-tuning. For more information, please visit our website. Thank you.
All right, so we still can have questions. Do we have any? Oh. You showed up. Any question for the author? All right. I guess you are all waiting for coffee instead of questions. Just one quick question for the author. So if we get additional data for training, how would you be able to update the controller?
Right. So you mean like if we add like more additional data, like either from the same set of environments or more diverse environments into our the offline data set? How
Yes.
in an online manner, or like
can you update incrementally, or you have to retrain from the beginning?
Right. That's a really good question. So if we have like additional data, we can just use the exact like offline RL algorithm to update like the policy and then adapt to new tasks. We didn't run such experiments in the paper, but we believe like this will further increase like the robustness and of the policy and enable like further improve the performance for fine tuning. This will be it will be very interesting future direction to explore like how we can run this in increments like online or lifelong learning paradigm, like when we have like use the data collected from this downstream task and continuously add that to the offline data and see how the performance will further improve as we have like adapt to more and more target tasks.
All right, thank you. That ends this session. Let's give our all authors one final round of applause. Next is a coffee session, and please come back at 3:35 for the next session.